Example 2.3. Three very large square planes of charge are arranged as shown. From left to right, the planes have charge densities of 1, 2, and 3, that is eta 1, eta 2, eta 3 of the given values and signs. Find the total electric field, direction and magnitude at points A, B, C, and D. Assume the plates are much larger than the distance AD. In other words, we're dealing with infinite planes. We have three infinite planes, infinite charged planes, not plates, but planes. It's the same thing. And are asked to determine the net electric fields at points A, B, C, and D. Let's draw the superposition fields while remembering these fields are independent of distance from the plane. So let's start drawing them. So I'm going to imagine that I have one, let's say this big. And that's going to be eta 1. And when I look at that, according to what the problem says, this is a negatively charged plane, infinite plane. And then I have my middle plate, and this one is positively charged. And this is plate 2. And then finally, I have my third plate. And this guy is negatively charged as well. And they all have uniform charge density, but this is the third. So if they're infinite planes, then that means that they're independent of distance. So then that means that here, that's a negative plate, so that field must be going like this. And then this field must be going like this. But it also is here and here. So now if I look at the field produced by charge density 2, well, that field goes in this direction, away from the plate, but it goes in both directions. That means going to the left and going to the right. And then finally, I have this guy, but this guy is a negative plate, so that has to start at the plate and move out. And so that's going to be my fields, the superposition fields. So then I'm going to have A, B, C, and D. So now because they're electric fields, I have to define a direction. So I'm going to say that I'm going to choose my axis. So that's my positive direction. That's my negative direction. Now let's talk about this before we move on. What you might find unsettling is that field E1, by the way, I could have picked E2 and E3, is not affected by the presence of the charged planes 2 and 3. That is, you might think that one infinite plane should not be able to penetrate another charged plane. That's a misconception. If you think this way, it's most likely that you believe that an E field represents some kind of substance or flow of fields. This is a misconception. Once the fields have propagated, which they do at the speed of light, there is no more propagation. It is a fixed field. In this case, it's a constant fixed field, and those lines penetrate. So now if I go back and I look at what I have here, it might be useful to actually copy this and bring this down. So let me copy this and bring it down here and just say, now what I want to do here is that now I'm going to apply superposition to determine the net electric fields at points A, B, C, and D. So before we get started, I just want to show you one trick, is that if I have 1 over 2 epsilon, I can multiply 2 pi and divide by 2 pi, and I have done nothing. However, I now get 4 pi epsilon divided into 2 pi. But I know what 1 over 4 pi epsilon is. So now, let's go look at the fields here. So here's the picture of the fields way over here. So I want to calculate these fields. So I'm going to calculate one in detail, and then the other three, B, C, and D, I'm just going to summarize. So let's look at the field at A. So the field at A, so if I look at A, you could see that the red is pointing in the positive, the blue is pointing in the negative, and the green is pointing in the positive. So when I look at superposition, I get plus 1 minus E2 plus E3. So if I start looking at this, this is then, it's going to be eta, 1 over 2 eta, but I can replace that by 4 pi epsilon into 2 pi. And so this then gives me eta 1, eta 2, plus eta 3 with that sign convention. Now note, we have employed the vector nature of the E fields. So when I go in and I look at these guys, I'm only looking at the magnitudes of this. So then eta 1 is 0.50 microcoulombs per meter squared. Eta 2 is 0.10 microcoulombs per meter squared. And then eta 3 is then going to be 0.35 microcoulombs per meter squared. So if I punch everything in here, then I'm going to get a result that reads 2 pi times 1 over 4 pi, which would then be 8.99 times 10 to the 9. And this would be Newton meter squared Coulomb squared. And then I get values of 0.5 minus 0.1 minus plus 0.35, and this would be in microcoulombs per meter squared. So when I get that number, I'm going to get positive 4240 Newton Coulomb, and that's going to give me the electric field at location A. The fact that it's positive, it means it's got to be pointing to the right. So now all I have to do here is to repeat the calculation. It's the same process. And we're going to do this. So now I'm going to repeat the same calculation for points B, C, and D. So using those numbers, I'm just going to go in and I'm going to look at this picture here. This is my guide. So if I look at this, then I'm going to say this here. What is EB? EB has, you could see that the red is in the negative direction. So I'm going to write minus E1. The blue is in the negative direction, minus E2, and the green is in the positive direction. So if I compute this value here, I get minus 4240 newtons per coulomb. I do the same thing for C here. And so if I just move through this somewhat quickly, just by looking at the picture, I'm then getting this guy. And I get a value that now reads minus 280, 20 newtons per coulomb. Then my last one is ED, which then gives me minus E1 plus E2 minus E3 3, and I finally get a value of minus 4240 newtons coulomb. So now I have these electric fields. So now, if I modify these just a little bit, that is the sketch that we have, I could then say that picture-wise, the net fields are, so using these values, I'm then going to come in and go like this. Now I just got to modify these guys. So I'm going to take all of these out. So if I look at 1, you could see that 1 is in the positive direction. So then I'm going to have EA going in the positive direction. EB is going to go in the negative direction. EC is going to go in the negative direction. And then finally, ED is going in the negative direction too.